Thanks for tuning in. My name is Stuit and I'll be talking to you about the predictive value of contrast energies in emotional phases for access to awareness. Emotional expressions are important communication tools, and experimental psychology has shown that we can detect emotional expressions relatively fast compared to neutral expressions. For example, facial expressions or emotion are known to attract attention when placed among neutral expressions. When the expressions are masked, it takes less time to see an emotional face compared to a neutral face. This suggests more access to our visual awareness. However, not all expressions are thought to be equal in their influences on awareness and attention. For example, in the awareness literature, there's lots of evidence suggesting fearful faces are fastest. In the visual search literature, we see lots of evidence for an advantage for angry facial expressions. Such effects are thought to be based on behavioral relevance of the expression. However, when it comes to the relative advantage of a particular expression, results tend to be also a little bit mixed. So in the awareness literature, we see inconsistencies for positive valence expressions relative to negative valence expressions, meaning sometimes positive valence is reported as fastest, other times negative valence is reported as fastest. In the visual search literature, we also see mixed results, but now for happy versus angry facial expressions. And one particularly interesting study concerning this discussion is from Savage and colleagues, and they show that the direction of the effect depends on the stimulus set chosen for the experiment. Now, this suggests that the emotional content may not be the most relevant player here. So if it's not the emotional content, then what is it? Well, natural images vary in lots of domains. So in this project, I'll specifically focus on one of those domains, and that's its spatial frequency content and its orientation content, because they are known to vary in our sensitivity to them. So for example, medium-low spatial frequencies, we're more sensitive to them compared to high spatial frequencies. And we're also more sensitive to cardinal orientations than we are to diagonal orientations. In light of previous inconsistencies, differences in these spatial frequencies and orientations may prove to be quite relevant. So taken together, we want to know what spatial frequencies and orientation contrasts of facial expressions relate to faster access to awareness, and assuming that we can find those, are those contrasts related to the emotional content, or is it an independent effect? For our experiment, we presented two images of faces with different expressions, one to one eye, with two dynamic masks presented to the other eye. Now, using a mirrors in a dual monitor setup, we presented the images to corresponding retinal locations such that the dynamic masks were perceived first, and the faces were suppressed from awareness at the start of the trial. After a few seconds, perception will start to alternate, and we instructed participants to indicate via key press if the alternation started on the left or on the right of fixation. 23 people participated in the experiment, and they completed 500 trials each. So here we show the fraction first perceived on the y-axis with the corresponding expressions on the x-axis. We used happy, angry, and neutral expressions. We see an overall main effect of the expression, which was driven by a difference between the happy and angry expressions, and we find an overall happy. We find that this has a happy superiority effect, which is in line with what Savage and colleagues reported, but is not in line with what Hansen and Hansen reported. So at this point, we're only adding to this inconsistency. So let's move on to our main analyses and see if we can make some more sense of our data. For our main analyses, we'll try to find the contrasts that matter, that have predictive value for which images will be perceived first. First, we converted the images to Fourier spectra, and here in this image, more yellow means more contrast. The distance from the center indicates the spatial frequency, with the lowest in the center, and the angle indicates the orientation of the contrast, with contrast along the vertical axes corresponding to vertical edges in the image. We ignore phase information and we downsample the spectra so that we only have the global contrast of the images left. We do the same for the other image and then combine the two spectra and add a label indicating which image was perceived first, the left or the right image, and we repeat this process for all trials of all participants, resulting in a data set of about 10,600 entries. This then served as the input for machine learning. We used a tenfold cross-validation procedure where within each fold, the wrapper method tries to find spatial frequencies and orientations relevant for prediction based on a trained data set and then test its performance on a separate part of the data. During training, we remove left and right biases from the training, meaning that if participants simply tended to report seeing the left image first, the wrapper can't learn from that bias. It can only learn from information within the images. Essentially, this means that we get 10 models for decoding what's perceived first, and we look at the performance and we look at the contrast used within those models. Based on the permutation test, we see significant predictive value of contrast for access to awareness, and we see that the contrast that was used was from the vertical edges in the images. So, are these contrasts related to the emotional content? Well, to answer that bigger question, because that's really what this is about, we first performed the same analysis on the same participants in the same paradigm, with the only difference being that the two faces now had the same emotional content, so they only differed in the actor. Here we find that we can also predict the access to awareness with the same accuracy and with the same features. So even without differences in emotional content, we can still predict what's perceived first. Now the question that we're left with is this related to, it can still be related to emotional content in some way. So to test that, we looked at the features relevant for distinguishing happy, angry, and neutral faces. When we use the same decoding method, but now try to decode these emotional expressions based on their spatial frequency and orientation contrasts, so not using any access to awareness data, we find that the most relevant contrasts are from horizontal edges in the images. Note that this is in line with previous reports on expression decoding. This shows that the main features for decoding the expressions are not the same as the main features for decoding access to awareness. However, the main features for decoding access to awareness may still contain some information regarding the expression, so we next looked at that. And to do that, we used those features found relevant for predicting access to awareness as the features to try and decode the expressions with. Here we find we can still do that, so there is some information on the emotional content left in those images. Now, if we take that with our behavioral effect, we would suspect that there is some predictive value of emotional content in our data set. So let's look at that a little closer. To investigate this, we looked specifically at the predictive value of expressions in our data set. And in a nutshell, we again split the data in test and train data. We tried to predict which image in a particular combination of two images in the test set would be perceived first, based only on the biases that we see for that particular combination in the train set. So for example, for the combination happy and angry faces, the happy faces if the happy faces are most often perceived first, we would predict in the train data, we would predict that happy is also perceived first for all trials in the test data. We did tests for each combination separately, and we found using tenfold cross-validation procedure that it was not significant, meaning that the emotional content held no predictive value in our experiment. So to recap, we find that we can predict which facial expression will be perceived first. The contrast energies that make this possible are not the most relevant contrast energies for decoding emotional expressions. However, so they do contain some emotional content. Still, behavioral biases for emotional content show no predictive value in our data set. So, even though we find a behavioral effect of emotional content, it has no predictive value. The spatial frequencies and the orientation contrast do. In specific, it was the vertical edges that made the decoding possible. So they appear to be most relevant for access to awareness. And this is in line with a previous study found, or at least we can say it's possibly explained by a finding from De Angelis and colleagues that showed that there's increased sensitivity for vertical edges when the two images presented to the eyes are different between the eyes, as was in our experiment. So as a take home, what I would like you to take home from this is I suggest we focus more on the predictors. Find the predictors. Find the predictors of behavior and their relationship to the defining features of your conditions, rather than just testing the behavioral differences. I think this will lead to more insight into into the data and may help some of these inconsistencies that we see in the literature. If you like these methods, have a look at my OSF site. I'm building a toolbox to make this very accessible and easy for everyone. It's under review, so there will probably be an update if we pass it. But you can have a look now. Any questions, I'll be around, and otherwise contact me. Thanks for your time.